let's just jump right in. And we'll start by acknowledging that we live in this situation of great expectations for AI. Obviously, people are very excited about the field, and buzzwords are thrown around. And unfortunately, this can create a situation of confusion or hype or fear of missing out. So today, I also hope to clarify some of these terms that we keep hearing over and over and talk a little bit about how they fit together. So let's start with the big term, artificial intelligence. So what is AI? Obviously, we know that in pop culture, it's usually depicted as killer robots or something like that. But the general perception in the public is that AI is very new, very cutting-edge stuff. And actually, the idea of creating an artificial intelligence is a very old idea that goes back at least thousands of years. We know, for example, that in ancient Greek mythology, there was a character called Talus, who was not a god like most characters in Greek mythology. He was an AI. He was a giant automaton made of bronze. And since then, we've seen countless examples in the literatures of many different cultures where people dream of this idea of creating intelligent machines. A more recent example is Frankenstein's monster from Mary Shelley's novel of 1818. So what's interesting is, how did we go from this situation in which people are dreaming with the idea of creating artificial intelligence for thousands of years to the situation in which we are now, where we have a clear and tangible path to reality with practical applications. And this shift started happening in the 1950s with the work of Alan Turing. So Turing was a brilliant British mathematician. He became well known during the Second World War for his work in code breaking. Some of you may have seen a movie telling the story of his involvement in the war. But after the war, Turing became fascinated with this idea of creating artificial intelligence. And in 1950, he published a paper where he sort of laid down the foundations for what later became the field of AI. And in this paper, he asked an interesting question. He asked, can machines think? And he realized that's a very imprecise question. So instead, he decided to formulate his question as a game that he called the imitation game. And the game is played by having a computer basically texting back and forth with a human. And if the computer can trick the human into thinking that they're talking with another human, then the computer wins at the imitation game. Now, this is known as the Turing test, and it's become a gold standard for measuring intelligence in machines. So since this early work of Turing in the early 50s, people got very excited about the field and started doing interesting work around these kind of ideas. And a few years after this, in 1956, the top researchers in the field got together for an entire summer at Dartmouth College to discuss findings and lay down a roadmap for what needed to happen in future years. And this was the first time that the term artificial intelligence was coined over the course of this workshop. And one of the attendees at this workshop, Arthur Samuel, had a brilliant insight. So he realized what they were trying to do was to create computers that could simulate the way they believed the human mind thinks. So that is, they wanted to make algorithms that can process symbolic information, that can make analogies, that can create metaphors, that kind of thing. And Arthur Samuel realized that what computers are really good at is arithmetic, number crunching. So he went back and he thought about this for a while. And a few years after the workshop, he came back and coined the term machine learning to describe his very specific approach to AI that was based on using mathematical algorithms to find patterns in numeric data sets, and then using those patterns to make predictions or decisions. So using this approach to AI, he created a computer that could learn to play the game of checkers. And what he did is he had this computer play an enormous amount of games against itself, and then analyze the data set of all these games to find patterns in all the moves, and then be able to make decisions in future games about what moves to make. And the computer got so good at playing checkers that eventually it was able to beat Arthur Samuel at checkers, and he was a good player. So that was pretty impressive. And so the question is, how did this approach become so powerful the way we know it today? Because I should mention that the machine learning algorithms, the mathematical ideas that we were using to find these patterns, those are not new ideas. We have things like regression, which is one of the most fundamental machine learning algorithms that we use today. It goes back to mathematical ideas from the 1800s, back when Gauss and Lejeune were thinking about these things. And even some of the most cutting-edge algorithms that we use in machine learning today go back to ideas that were developed in the 1950s. So obviously what happened is that suddenly we got a lot of computational power, and the internet happened, and we started amassing very large data sets. And in the late 90s and early 2000s, some of the world's tech giants started very heavily investing and believing in these ideas and pushing the field forward. So let me walk you through a few milestones that got us from that in the late 90s and early 2000s to where we are today. So in 1997, IBM built a computer called Deep Blue. They beat the world's best chess player at chess. So Garry Kasparov was the best chess player in the world, and he lost to Deep Blue. Let me tell you another personal story. So in 2003, I was working at a physics lab in Hamburg, Germany, and we had this particle collider. It was a big underground tunnel, 7 stories underground, and we were basically making particles, subatomic particles, crash against each other at incredibly high speeds, and we had these detectors to measure what was coming out of these collisions. And the problem we had was trying to classify what things we were seeing in the detectors. It was a very difficult nonlinear classification problem, and we were using artificial neural networks to do this classification problem, and we had incredible success. We were being able to classify what we were seeing very accurately, but the way we were doing this, it was incredibly time-consuming, incredibly manual. We were writing C code from scratch to describe the architecture of these deep nets and to describe their activation functions and so forth. So it was very time-consuming work, and this was happening with success in research labs around the world. But it was nothing like what we have now, where it's so easy to do this kind of work, and many companies are doing it in much shorter time frames. So a few more things had to happen to get us to where we are today. One of the big things that happened a few years after that, in 2006, Geoffrey Hinton and his team published this paper that was groundbreaking at the time. And basically, they had incredible success doing image recognition. So what they did is they had this very large set of handwritten numbers, like what you see in this picture, and they trained machine learning algorithms to be able to say what number they're looking at. And the accuracy that they achieved was comparable with human accuracy for the first time. So this made people incredibly excited. A lot of researchers started believing in the promise of image recognition using machine learning, and it created an explosion of activity. And there was, more importantly, an explosion of open source frameworks that started being created. So what happened was that researchers would write a lot of code to work on a project, and they would release their code as open source projects that then other people could build upon, and it created a kind of compounding effect of very interesting results happening very quickly. And as this was going on for a few years, we were lucky enough to have this wave of machine learning superstars who also happened to be masters of public outreach and masters of marketing. And they were really responsible for bringing these ideas out of academia and out of the research labs where they were being developed into the public. And that got everybody excited about machine learning. It became a very hot topic as it is today. A few more interesting things that have been happening since. In 2011, IBM's Watson beats the world champions at Jeopardy. So again, very, very big, because we had already had all this success with image recognition, and now suddenly we have the ability to do natural language processing. So we have computers that can understand a question in English and then find out what the answer to that question is by reading a bunch of Wikipedia articles and then formulating an answer and spitting it back in English. So very big milestone. And a few years after this, Google's DeepMind beat the best Go player in the world, or one of the best players in the world at Go. So again, Go was considered a very challenging game for computers to play, more challenging than chess, and it was widely believed that computers were never going to be that good at Go, but that this was achieved in 2016. And I want to show this from 2017. This machine learning book was published, and it became very popular among practicing engineers. And in the book, they talk about this machine learning tsunami phenomena. So it's basically this idea that we're drowning in data, and if we're smart about how we're analyzing it with machine learning algorithms, we can get a lot of insight and a lot of value. And because of this, we now see this tsunami of machine learning applications everywhere around us. So now we come to the era in which we are today. Basically, machine learning has snuck its way into everybody's personal life. And there's several applications that we're all feeling the impact of. So for example, we have things like image recognition. Google Photos automatically tagging pictures of the people that you know. You don't need to put a password on your phone to unlock it. You just look at it and it unlocks itself. We have things like voice recognition. There's Alexa and Siri. We can talk to our phone, we can talk to our car, we can talk to our house, and machine learning algorithms are listening, ready to follow our commands. And then we have things like recommender systems. Everyone is making decisions on a nearly daily basis about what to watch on TV or what to buy online based on recommendations that come from machine learning algorithms. So we're all familiar with the power of these technologies and these techniques, and we're feeling it in our personal lives on a daily basis. So now we come to this era of data science and industry, where we know that there's a lot of promise in this, so we want to run our companies using these techniques to have better outcomes. Now, data science is obviously a very broad field, so when people are talking about doing data science, they could be talking about a variety of things. They could be talking about building data pipelines or doing data visualizations, doing traditional statistics, doing data wrangling or data munging, or doing machine learning. So when we talk about AI, what we usually mean is doing machine learning. So what is machine learning? Well, remember that Arthur Samuel coined the term back in the 1950s, and it was this approach to doing artificial intelligence by using math to find patterns in numeric data sets and then make predictions or decisions based on those patterns. So let me give you a very brief definition of machine learning. Machine learning is the art or the science of programming computers so they can learn from data. Okay, so we know that we've seen all the successes in things like image recognition, voice recognition, even self-driving vehicles, and also playing video games. Computers have gotten better than humans at playing a lot of difficult video games. So what about in business intelligence? This is where my focus is. I work for a company that sells software to do machine learning, specifically in the BI world. And business intelligence, it's the same idea. We have this idea of taking mathematical algorithms to consume BI numeric data sets and find patterns in those data sets to then make useful business predictions. So let me give you a very concrete example of how somebody can solve a BI problem using machine learning. So let's consider this hypothetical software as a service company that sells monthly subscriptions to an online platform. And this company wants to understand customer churn. They want to understand which of their customers are canceling their service. And they want to be able to understand what drove churn historically, and they also want to be able to predict customers that will churn in the future. So the natural way to do this is to collect a data set of historic customers. For instance, in this data set, we have every row representing a unique historic customer, and every column represents an attribute about this customer. So we have something like churn 1y, which is, did this customer churn yes or no during their first year as a customer? And then we have a bunch of other columns describing more features about this customer, like their customer ID, their gender, their age, their zip code, et cetera. So the goal is to be able to predict this column using patterns that we find in all the other columns. Okay, so simple enough. We can go and look for patterns. And there's very simple patterns that we could notice at first sight. For example, all customers over the age of 70 very rarely churn during their first year. Then you can start finding more complex things like females who are in their 40s and on a family plan almost never churn after the first year. Or you can find even more complex things like males who are in their 30s and on a personal plan, they depend. If they happen to have logged in less than 20 times in their first month, then they are very likely to churn after a year. But if the same males in their 30s on a personal plan happen to have logged in more than 20 times in the first month, then they very rarely churn in the first year. So imagine trying to find patterns way more complicated than these ones on huge data sets with hundreds or thousands of columns. That gets to the point where you can't find those patterns with the naked eye or by visualizing this data set in any way. And that's where machine learning really shines. It could find all these very complicated patterns over many columns in a very large data set. So once you've found those patterns, then you can go and make predictions using those patterns. For example, if you get a new batch of customers who just reached their 1 month mark as a customer, you can say, well, here's a customer who's over 79, so this person will probably not churn after a year. Here's a female in her 40s on a family plan. Again, this person is not likely to churn. Here's a male in his 30s on a personal plan, and he logged in less than 20 times in the first year, so very likely to churn. Okay, so the idea is very simple. You have a table of data. You pick a column in this table. That's the column you want to predict, and you want to find patterns in all the other columns to predict this target column. Now, the way you find these patterns, that's where it gets technical. There's many mathematical approaches to do that. There's algorithms that could be based on linear models. They could be based on decision trees. You could have ensembles of models or artificial neural networks. The approaches are very elaborate and very varied, but the basic idea is a very simple idea. It's predicting one column using patterns found in the other columns. This is what we call supervised machine learning. And the cool thing is that many practical questions can be phrased in this way. So back to this business of finding patterns in data, this has significantly evolved in the last few years. So we used to have to write the mathematical equations and algorithms and understand which ones were needed to solve a particular problem. And then we had to be able to translate these equations into code and write that code and execute it to find these patterns. But then there was this wave of open source software that allowed us to be able to solve these problems by writing significantly less code. So now we didn't have to write the algorithms from scratch. Now we could just use the library and use that as part of our code, and it significantly reduced the amount of time and the amount of code that we have to write. But it still requires some expertise and knowing how to write at least some code and how to know what algorithms are relevant for what problems and that kind of thing. But now we've entered into this era of automated machine learning. This is what I do for a living. I work for a company that sells a platform that does automated machine learning. And what this does is that you basically connect the data set to this platform and you say, what do you want to predict? And you just point out what you want to predict, and you push a button and everything happens automatically. The data is cleaned. The data is used to train a wide variety of algorithms. They're all tuned for your data set, and you get a list of all of them, and we suggest this is the best one, and it's used to make predictions. So this entire very technical process that used to be the ceremony of training a machine learning model is now reduced to the push of one button, and everything happens automatically. So what's interesting is that, okay, we live in this era where it's easier than ever to train machine learning algorithms and put these models into production. So why do we keep hearing things in the news all the time that sound like this? Failure rates for analytics or BI or machine learning projects, 85%. Failure rates for BI or machine learning projects, 85%. Failure rates, 85%. First of all, it's amusing to data scientists to think about how they come up with these numbers. But anybody who's worked in the trenches of data science knows that there's some element of truth to this, because I've worked in the past for several companies and worked on projects that never saw the light of day. So we're familiar with this idea. Why is this happening? Here's one thought. In practice, business questions are very varied. These are some real questions that some of our customers come to us with. For example, we want to predict the lifetime value of a media fan. So you have a person watch a movie in a theater in one city, and then the next week they buy a piece of merchandise in a different city, and then the next week they sign up for some streaming service in their hometown. How do you define or even measure historic lifetime value for customers, let alone how do you predict it for the future? Or you have somebody come to you saying, hey, we have 30 factories across the country. We want to optimize the production of our factories. Or we have this many warehouses in these states. How do we optimize warehouse storage space? So translating arbitrary business questions into machine learning problems may be tricky. Then this is where the big distinction exists between machine learning in school or in Kaggle competitions or in academic projects and machine learning in business, in the real world. When you take a course on machine learning or you learn machine learning from a book, you typically get problems that are really well defined, and you get a data set to work on this problem, and you just spend all your time just fine-tuning your algorithms. So for example, the ImageNet competitions, or if you join a machine learning competition where they say, we're going to give you pictures of bananas, and you have to train an algorithm to tell us how many bananas are in each picture. It's a very well-defined problem. All you have to do is spend time fine-tuning the algorithm for this use case. Or they can say, I'm going to give you pictures of animals. You've got to train an algorithm to tell us what kind of animals are in the picture. Again, very well defined. In business, it's a totally different beast to do machine learning. You have to do this translation of an arbitrary business question into a machine learning problem. Now, this is an article that I saw online not too long ago. AI is not magic dust for your company. This is Andrew Moore. He's the head of Google Cloud AI. This is so interesting to me, the head of Google Cloud AI talking about how difficult it is to do this. So he says getting the technology to work in business is a huge challenge. Here's a quote from an interview with Andrew Moore. Sometimes I meet very senior people with big responsibilities who have been led to believe that artificial intelligence is some kind of magic dust that you sprinkle on an organization and it just gets smarter. In fact, implementing artificial intelligence successfully is a slog. So why is it so hard? Here's another quote from Andrew Moore. He says the most common mistake he sees is people come to him saying something like this: I've got a massive amount of data. Surely there's some value I can get out of it. Okay, so this is this idea that you have a huge amount of data and you're going to plug your data into some magic artificial intelligence system that's just going to magically give you insights and tell you how to run your company and basically do everything for you. So if this is silly and we know it's science fiction to think of this as being a reality, then what should we do instead of this? And the answer is very simple. The answer is find a problem that you have. So you know your business better than anybody. You know what problems you need to solve. And think of something, a problem that your customers have or a problem that your workers have. And once you've defined that, what you do is you work backwards and you say, okay, if I could wave a magic wand, what would the solution look like? And then you sketch out a path to get to that solution. And then you say, okay, now that I have a path to get there, what parts of this path are time-consuming or are expensive? And what parts in this path can I automate? So then you work backwards from there. What kind of automation can support that? And then what you do is you work backwards from there. And you say, okay, what kind of data do I need to automate this specific path of the path of this part of a path that I already sketched out? And that's where you decide where to insert machine learning in this plan that you've made. So we've gone from this blue sky, crazy science fiction idea of machines just magically running your business for you to this more realistic idea of planning a path to success where at the end you have your magic wand solution, at the beginning you have raw data, and you've defined the steps that need to happen to get to where you want to get. So let me, this is obviously this is very different from the magical machine learning idea. This is fun, this is creative. You have to plan what you want to do. And I'll make an analogy with what happened in the world of BI. BI, there's tons of vendors that we're all might be familiar with selling us technology to democratize or automate traditional business intelligence. And what happens in a BI project? Most companies are implementing BI in some way. What happens is that you make a plan. You start with raw data at the beginning. Then you define steps of what needs to happen with this data. You have to clean up the data, do ETL. You have to set up some processes to validate that the data has good quality. You have to define business definitions that make sense for your company. And at the end, you visualize the results in some dashboard that are consumed by a wide audience. And then you start inserting tools for each step in this process to make that step easier. You buy a tool that does ETL. You buy a tool, you set up an internal process to do data validation. You buy a tool to do data visualization. With machine learning projects, it's the same idea. You have a path to success. At the end, you have some insight or automation that you want to achieve. And this is usually consumed by a wide audience. At the beginning, you just have raw data. And then you sketch what individual steps you have to take to get to where you want to get and define what these steps are. They could be doing ETL, data validation, machine learning. And for one aspect of this, like machine learning, then you can automate that with a tool that can take care of that. But you still have to understand the overall business strategy. You still have to understand the steps that we need to accomplish the whole. And then you understand which steps can be automated by what tools. And then it's just a matter of acquiring those tools to speed up that step in the process. So let me give you an example of a real problem that I worked in some years ago of not thinking a problem all the way through. I was working for a company that had a call center, and the goal, somebody thought it was an outbound sales call center. So we were just calling people to try to sell them something. And somebody thought it would be a great idea if we had a way of scoring these sales leads to say, oh, let's prioritize the ones that are more likely to convert. So my data science team, we built a lead scoring model for the call center. And it was actually a very good model. It could sort leads in order from the ones that were more likely to convert to the least. And once this was all done, then we realized that the people at the call center actually had the bandwidth to call everybody on the list 10 or 20 times a day. So if you're going to call everybody, then why sort the leads? If you only have bandwidth to call 5% of your leads, then sure, let's rank them and make sure we call the best ones. But this is an example of not thinking the project all the way through and not knowing what you're going to use this algorithm for specifically and how it's going to add value. Like I said, I work mostly in business intelligence. And people have common business intelligence concerns like trying to predict which of our customers are going to churn. So you say, hey, I have information about my customers, and I want to predict who's likely to churn. So we know things like the gender, the age, the zip code of our customers. We know the date when they signed up to be a customer, and we want to predict when they're going to leave us. Sure, we can build a model to that, but how we can try to find some loose relationship between where they live and their gender and when they're going to leave, but it's probably not going to be a very strong relationship. I mean, if you sell something like streaming service to skiing videos, maybe people sign up in the winter and then cancel in the summer, so there might be some loose relationship with the date in which they signed up. But very often, the data sets that we have for business intelligence are not data sets that have huge predictive power. This is not like an image recognition problem where you want to say what's in a picture, and all the information to make that decision is in the picture. This is an incomplete data set that only has a very narrow slice of what your customer is like. So when you build a model on these kinds of data sets, sometimes you have mediocre scores on these models. They're not super predictive, and you can't necessarily trust each individual prediction. But if you are clever about how you're consuming these predictions, you can still get a lot of value from these models. So for example, I'm going to give you an example of a project that did something like this. This is this idea of hiring with machine learning algorithms. So there's companies that do this for a living. They basically work with companies to help them hire applicants for high volume positions more efficiently with machine learning. So if, for example, you have a situation where you have one opening and 400 people apply for that position, and you need to hire somebody in a week or 2 weeks. So you don't have time to sort through 400 resumes that quickly. What they do is they can have all these people take a video interview and then do machine learning on these videos to try to predict who are going to be the ones you should focus on, or do machine learning on their resumes to try to predict who's going to be the best candidate. So if you train a machine learning algorithm to predict something like this, and let's say that historically you know that people who apply for that position, there's only 1 in every 12 that you actually like. So it's not very common to find top performance in the applicant pool. So if you train a machine learning algorithm to predict who's going to be a top candidate, maybe there's not a lot of predictive power in just a resume or just a video that's 5 minutes long to try to know if somebody's going to be a top performer. The machine learning algorithm seems mediocre on the surface. You can't necessarily trust it for one prediction. If it tells you you should hire this person or not, you can't trust it for that specific case. But you can trust it in aggregate because you can maybe show mathematically that if you run the algorithm to sort people and then get a curated sample of applicants, then instead of having 400 initial applicants, you get a curated set of 100 people. But in this set, 1 in every 4 are people that you are very likely to like instead of 1 in every 12. So then you're delivering tangible value to the company because you say, now you don't have to look at 400 resumes. Now you only have to look at 100. And now the probability of finding somebody you like is slightly higher or 3 times higher than it was in your original sample. So this is a perfect example where the score of the algorithm is not necessarily impressive. You can't necessarily trust it for one prediction, but you can trust it in aggregate if you find a clever way of using the aggregate predictions. So let me just summarize the main ideas of what I talked about. First of all, AI has had a very long and interesting history. The evolution of how we train a machine learning algorithm has changed from having to write down the equations from scratch and write the algorithms from scratch to using open source libraries to using automated machine learning platforms now and just doing everything with the click of a button. Now, the idea of creating a whole machine learning project, it's important to plan it all from start to finish and know which steps of the process can be automated by machine learning. And finally, you might be dealing with data sets and business intelligence that are not super highly predictive, but if you're clever about how you're using these models, you can get a lot of value out of that. So that's my talk. Thank you.
The tool that you have that provides the UI for machine learning, looks like it does all the processing. Is that locally?
So it depends on if you want to do it in the cloud or on-prem. So there's 2 versions. You can do it in the cloud where it's a SaaS platform. You log in and everything happens in AWS. Or if you want to do it on-prem, it'll happen in your servers.
At the beginning, you showed like the robots that everyone gets scared about. You know, they're going to take over the world. And that's like the number one question I get from people who don't understand it is they're like, oh, robots are going to take over the world and be our overlords. What's your response to people who are scared of this technology and where it's going? Because that's what they're seeing, not all of the math and stuff that goes into it.
Yeah. One time I heard somebody say, well, what are we going to do if robots take over the world? And they said,
Like,
well, just split water on them. Spill a cup of water on them. And I think, was it Andrew Ng that said that it's like worrying about overpopulation in Mars right now? We haven't even colonized Mars yet. There's many opinions on this subject. And I think there is definitely a lot of danger. Robots taking over, we're so far from that in my mind that it's not really a concern, but there's definitely a lot of things that we have to be very careful about with the way algorithms give us results that could be adversely impacting certain groups of people. The hiring example that I gave earlier, companies that work in this space have to be extremely careful about mitigating bias with algorithms. Algorithms can very easily get racist or sexist or whatever, and you have to be very careful about, sometimes you have to purposely make the algorithms less accurate to make sure that they're completely blind to features that identify a certain group of people, and they're not using that in any way, even if it's very indirectly, to make a prediction. So it's just about being very careful of the different use cases and how that could have adverse impact if you're not paying attention to those details.
So kind of keeping the human element in it.
Yeah.
Thank you.
Yeah.
Since you were showing a little bit of the tool that does the automated machine learning, how easy is it to understand, to interpret the results, to know if there's bias built into the model, and to know if there's a better way of using the data than the way you started?
Yeah, so that's a good question because to the point we just made, you always need a human in the loop to look at things like this because the platform doesn't know what the column names mean. You have these names for your data set, and what a platform like this can tell you is to say, hey, I'm predicting that this person is going to be a good candidate for this position, and it can tell you the reasons why it thinks that. So it'll give you a list of reasons at the individual row level. So if they say, hey, I'm suggesting that you hire this person because they have very pretty eyes, then you know that's not a good reason. But at least the platform is transparent enough to give you the reasons why it makes certain predictions, and then it's up to the human to interpret if those are valid reasons.
So as things become more and more open source and more treated like a black box, especially when you automate things, do you build in anything to help people debug problems or understand how that prediction is coming about?
Yeah, so this goes back to model interpretability. So in the case of our specific platform, we give you a feel for the model in general, what's driving predictive power for that model, and give you a list of ranked features. But also we give you interpretability at the row level, so if you can dig into a specific prediction and see why that prediction happened the way it happened. But then, again, those are just insights that are surfaced to a human user that has to, at the end of the day, make the decisions about if the model is being biased or not. So automating those things completely sounds dangerous and scary, and I think it's a good idea to have a human in the loop that can work in conjunction with this kind of technology, and at the end of the day, make the final decisions.
What kind of validation testing or effort goes into validating the models?
You mean like testing how it well? Yeah. So when you train them in our platform, you mean specifically? So we always test the score that is reported to the user is measured on out-of-sample data that the model has never seen before. So we do a standard cross-validation process where we divide the data set into different folds, and we're always testing how the model is performing on data that it hasn't seen before. And so that's pretty indicative of how the model will perform out in the wild in the future because it's making predictions on data that it's never seen.
Is that standard throughout the industry?
Yeah.
Yeah.